These next couple don't require any tricks, so I would recommend actually trying out parts B and C before you watch the video here on how to do these. Okay. All right, now that you've given it a try, let's see, what side do we want to start with? I am kind of looking at this side because I see that I could use a trig identity on that cosine of 2x or the cosine squared of x, either one of them. So that just seems like a natural place to start, so I'm going to do that. All right, and the next thing that I'm going to think about is, well, in the end, I would just like tangent of x. I don't want tangent of 2x. So let's try and get rid of the fact that we do have a 2x here by using one of our new trig identities. Okay, so cosine of 2x is actually equal to a few things, right? If we go up, let's go look. So we'd be actually looking at the underlined formulas here. So cosine of 2 theta is equal to all these other things here. Now, let's go back and see if we can figure out which one of these might be the easiest one to use for us. So I can see that in the end, I would like to end up with a 1 here. So what that would mean is if I were to use a formula here, I would really like it if there was a cosine squared of x here, and then plus or minus something. And that's because cosine squared of x divided by cosine squared of x would give me the 1 that I'm looking for. So let's see if any of the identities start out that way, cosine squared of x. Here we are. And actually, the first version of this does. Cosine squared of theta minus sine squared of theta. All right, so let's go back and apply that. Here we are. So we have cosine squared of x minus sine squared of x. If you chose to use one of the other two, this will still work out. It just might take you an extra step or two, which is not a problem. So next, we'll split the numerator. Remember, we cannot split sums and differences in the denominator, but we can in the numerator. And all I really even mean by splitting the numerator is we're kind of doing the reverse that we would normally do if we were going to subtract two fractions here. Right, you can see that these do have a common denominator, so if we were to subtract them, it would look like this up here. So this is all good here. And then next, well, cosine squared over cosine squared is 1, and sine squared x over cosine squared x is tangent squared of x. And we are done with that one. Let's go look at the next one. So here we have sine squared of theta over 2 equals cosecant of theta minus cotangent of theta all over 2 cosecant of theta. And once again, we need to pick a side to begin with. And I think in this case, it's actually a little bit easier to start with this side. If you ever don't know what to do on a problem, sometimes a good route is just to rewrite things in terms of sine and cosine. But before I do that, because I am going to go in here and write things in terms of sine and cosine, but before we do that, let's maybe split up the numerator like we did before, the previous example. So we have cosecant of theta divided by 2 cosecant of theta minus cotangent of theta all over 2 cosecant of theta. And if we do this, you can see over here, all we're going to be left with is a 1/2. But this one here, we'll want to rewrite this in terms of sine and cosine. So cotangent of theta is cosine of theta over sine of theta. And then this is all over 2 times cosecant of theta. So that's 2 times 1 over sine of theta. All right, let's go ahead and flip and multiply. So we have 1/2 minus cosine of theta over sine of theta times the reciprocal of the denominator, which is sine of theta over 2. And you can see that the sine thetas cancel. And so all we're really left with here is 1/2 minus 1/2 cosine of theta. And this might look familiar to you, and if it doesn't, let's see why this looks familiar to us. If you pull a 1/2, so factor a 1/2 from these two terms, you'll be left with 1 minus cosine of theta. Now does this look more familiar? Maybe not. If it doesn't, let me remind you of what we're looking for here. We actually know that sine squared of x is equal to 1 minus cosine of 2x all over 2. So this doesn't quite seem to match this here, right? Because we don't have a 2 theta in here. But that's actually okay. If we were to let, say, x equal, let's do theta over 2 or 1/2 theta. Either one of those would be fine. You could see then that, well, this would look like sine squared of, and again, we're replacing x here with a 1/2 theta. And that would look like 1 minus cosine of 2 times 1/2 theta, which is just theta, and then all over 2. And that should equal sine squared of 1/2 theta, or if you prefer, theta over 2. So we started with the right-hand side. We used a bunch of algebra and trig identities and ended up with the left-hand side of the equation. We have verified this identity. Let's try one more. To begin this last one, I think any side here would be a good side to start with. And I think a lot of you actually are going to choose this side this time around, although starting with the right-hand side is great too. Let's start with the left. So if we start with the left, we might remember that tangent of alpha over 2, but we remember that tangent of alpha over 2 is part of one of our trig identities. Let's go up and see which ones. There's actually a few. That's not the one. Here we go. So we have our tangent of alpha over 2 here, and it is equal to 3 different possible things. Okay. Now, note the original problem already has a 1 plus cosine alpha in the denominator. Okay. So we want to somehow go from 2 times this thing to something that has this as a factor in the denominator. Okay. So I like starting with that. Let's just start off with tangent of alpha over 2 is equal to sine of alpha divided by 1 plus cosine alpha. And we're there. So this is then equal to 2 times, and in the numerator, right, we had sine of alpha And in the denominator, we had 1 plus cosine of alpha. And again, we're already part way there. We already have the 1 plus cosine alpha in the denominator. I do notice something else here, though. So the other factor in the denominator is just sine of alpha. Why don't we try and multiply the numerator and denominator by that? See if it fixes our problem. And if we keep going here, looks like we have 2 times, then we have sine squared alpha. And in the denominator now, we actually have exactly what we wanted, which was a sine of alpha times 1 plus cosine of alpha. And notice as well here, on this right-hand side, there isn't a 2 out front, is there? So let's bring our 2 in the numerator with the sine squared alpha. So 2 sine squared of alpha. Let's think about what 2 sine squared of alpha really means. Well, that just really means we have sine squared alpha plus sine squared alpha. And the reason I'm pointing this out is I see that we have a sine squared alpha here. So let's just break that into 2. So then we have sine squared of alpha plus sine squared of alpha. And then this is all over sine of alpha times 1 plus cosine of alpha. And we're even closer now. We have everything looking good except for this piece right here. Well, this piece that I'm pointing at right here is equal to 1 minus cosine squared of alpha. That's using one of our Pythagorean identities. All right, and we have now verified this identity.